Well, hello there folks, I hope you're doing well. In this video we're going to be talking about chapter 6.4, Functions. You can find this on page 305 of your textbook. There are a special class of relations, the ones that the class we talk about the most, and this class is called functions. Function is a relation where two quantities depend on each other in a particular way. If you look at these first four examples here, these are all functions. However, it's easier here. Looking at the bottom four examples, they are not functions. Well, what's the difference between them? You can see, for example, the third one here, it looks almost identical, it's just this one's been rotated. And for these dots here, it looks very similar, but these two dots have been brought straight in line with the first dot. So what makes a function a function? A function is a relation where each value of the independent variable is associated with exactly one value of the dependent variable. In maybe in easier terms, there is only one x value for each y value. If I look at it, or no, sorry, better said, there is only one y value for each x value. That's what I meant to say. If I look right here, for example, every single x value, if I go up and down to the y's, only has one possible y value. So even here, every single x value only has one associated y value. If I go over here, though, for this circle, for example, x is equal to 0 has two possible y values, the one in the positive and the one in the negative. For these dots, this x value down here has three possible y values. For this graph here, or this relation here, there's two possible y values for each x value. For this one, there's like four possible y values for each x value. So anytime there is more than one possible y value for an x value, it's not a function. Why do we care about functions? Functions can be written using function notation. So where it's y is equal to something. And the y can be replaced with an f and bracket x. This tells us that it's a function named f, and we can solve for a variable named x. The way, and it's usually read as f of x or f at x. I'll usually say f of x. The way that we can check if something's a function or not easily is looking at the graph. We can just, assuming there is a graph, we can just put a line through it. Oh, I thought there was a picture. In your textbook, there is a picture on page 307 using a pencil to do the vertical line test. If your pencil is straight up and down and it goes through the line of the graph more than once, it's not a function because it means that an x value has more than one possible y value. And it's important to note that not necessarily every x value has to have more than one y value for it to not be a function. If even just one point on your graph, one x value on your graph, has more than one possible y value, it's not a function. And that's basically it. The nice thing about functions is that we can get a value for x and just plug it into our function, into our f of x. For example here, f of x is equal to 4x plus 1. I can plug in the x value of 2, because that's what they do here. So f at 2, and it only has one possible answer. F at 2 is equal to 4 times 2, which is equal to 8 plus 1. So f at 2 is equal to 9. So that means that in this function, if I were to graph it, where x is equal to 2, y is going to equal 9. The f at 2 is going to equal 9 or equal y. So let's do a couple of examples. For each pair of relations, decide which relation is a function and which is not a function. Explain your choice. A, right here, it looks exactly like the first example on the first page of this chapter. There is only one y value for each x value. So it is a function. Yeah, this one's a function. I'll even, let's get the old pen out And let's check things off. I was going to use green, but it's going to be confusing to try, or complicated to switch back and forth using this non-whiteboard pen. So yes, that is a function. B, if I look here, well, I have two possible y values for pretty much every single x value. So no, that is not a function. For C, C and D, I just have lists of graphs. For C, I have x is equal to 2 and y is equal to 5, but I also have x is equal to 2, or at x2, y 7, which means I have more than one possible y value for the same x value. No, C is not a function. D, I have -3, -2, -1, and 0. So I have 4 completely different x values. You'll notice the y values alternate back and forth. At x is -3, y is +3. Let me just try and sort of do this. At x is -3, y is +3. So right there. At x is -2, y is +4. At x is -1, y is equal to 3. And x at 0, y is equal to 4 again. Even though the y values are repeated, it's okay. The important thing is that for each x, I only have one y. And that's the case with these values that I'm given. So yes, D is a function. Basically, if I have it in a table, or in this next example here, if I have it in a set of ordered pairs, if the x is repeated at all in my grouping, so I have 2 2s here, or in this one here, 1 and 1. Actually, I got tons of 1s. 1 and 1 and 1 and 1. Not a function, not a function. But when I just have one of each x, 1, 2, 3, 4, yes, it is a function. So if we have the graph, once again, we just do the vertical line test. We check, is there only one x, or sorry, is there only one y for each x value? If so, it's a function. If we are given a table or a set of ordered pairs, we just check, is an x value ever repeated? If yes, no, it's not a function. If no, then yes, it's a function. If an x value is never repeated in a table or a set of ordered pairs, then it is a function. So now we can do an example with the function notation. The function f at c is equal to 1.8 c plus 32 is used to convert a temperature in Celsius to Fahrenheit. Determine f at 25. Explain your answer. So f at 25 is saying, what is the temperature in Fahrenheit if it's 25 degrees Celsius? And then the second part's a little more complicated. Determine c so that f at c is equal to 100. Explain your answer. We'll start off with A. It's really easy, and I could just pull over the solution, but I'm going to do it step by step. So I'll start by rewriting my equation. F at c is equal to 1.8 c plus 32. We care about when c is equal to 25, so that's what I'll write. I'll replace my c's with 25. So f at 25. And it's important to know, or remember, that f at anything is equal to our unknown value, the dependent variable that we're looking for. So f at 25 doesn't mean f times 25. It means the value of f when my variable, my independent variable, in this case c, is equal to 25. So f at 25 is equal to 1.8 times 25 plus 32. So I now go to my next step, f at 25, and I put it into my calculator. It's an easy calculation to do. 1.8 times 25 plus 32 gives me a value of 77. And it says explain your answer. It means 25 degrees Celsius is equal to 77 degrees Fahrenheit. That's what our function has told us. For each value of c, so for each degree Celsius, there's only one possible f. So yes, this is a function. For b now, it says determine c so that f of c is equal to 100. Explain your answer. So once again, I'm not going to rewrite the equation necessarily because we already just have it right up there. But for b, I need to know f at c when it's equal to 100. So I need to find out at what value of c are things equal to 100. When is 100 equal to 1.8 c plus 32? The first thing I'm going to do is subtract 32 from both sides. So subtract 32, subtract 32. 100 minus 32 is equal to 68. And 1.8c, 32 minus 32, of course, is just equal to 0. I'll try and extend my page. Oh, it worked. Wonderful. And now to get c on its own, the last thing I need to do is just divide both sides by 1.8. 1.8. So, I put in my calculator once again, 68 divided by 1.8, and it gives me the answer, 37.7, repeating. Repetan 7. And 1.8 divided by 1.8 is 1, of course, so I'm left with C. What does this mean? It means that 100 degrees Fahrenheit is equal to about 37.8 degrees Celsius. So there is an example where I can use a function to solve a question or answer a question. Either way, like I can go one way and I can go the other way and find the answer. Both ways is going to work. Our last example here, example number 3, is the graphing of linear functions. Sky has a cell phone plan for a monthly fee of $20 plus $15 cents for each text message to or from a number not on a list of favorites. You guys won't remember this, but I certainly remember this. It was awful. So you never wanted people to text you if you didn't know them, because that charged you 10 or 15 cents every time. It was horrible. Anyway, Sky's monthly bill can be modeled by the relation C is equal to 0.15 n plus 20, where C is the total charge in dollars and n is the number of additional text messages. Write the relation in function notation. B, make a table of values. Graph the function if Sky sends up to 4 additional text messages. C, if Sky's cell phone bill for a certain month is $22.25, how many additional text message charges are there? There are a few ways that we can do this. Do C, but we'll start with A. If I want to write it as a function, or write the relation in function notation, I am going to use, usually I'd use F yeah, they do something slightly different in their example. I don't really like it, so we're just going to use F once again. We're going to say F at n, because n is the number of text messages that we are concerned about. So F at n, the function at n, is equal to 0.15 n plus 20. So we've rewritten our equation, our yx equation, or Cn equation, as a function equation. The function f at n is equal to 0.15 n plus 20. So another way I could write this is the answer right there, but I could have also just said C is equal to the function n. Blah, 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 blah. So that's A. B, make a table of values to show how much Sky is charged. Well, that's simple enough. So we'll make the table of values. I apologize about the ugliness of the table. So our independent variable, our X variable, is N, the number of text messages. Our dependent variable, the cost, which I could also write as F of N, either way, is the overall cost. So we are going to do the table for 0, 1, 2, 3, 4. So it's 0 texts 1, 2, 3, 4. This is the old days once again. 4 texts a month, not not unreasonable, I guess. Anyway, so if she sends and receives no additional texts, it is $20. Or I guess, sorry, 4 texts to or from someone that's not on your list, your special 5 or whatever it was. My 5 was what Kudo called it. If she sends 1 text or receives 1 text, it's going to be an additional 15 cents. Another text is going to be another 15 cents. So it'll be 20.30, and etc. 20.45, 20.60. That's what our table is going to look like. It wants us now to graph the function. So graphing the function, I'm not sure why they decide to graph the first 16 values when it just says graph the first 4, but in the textbook, now I'm going to bring up the textbook. In the textbook, there's their table. You will see the graph for the first 16 values for 1 to 15 additional, or sorry, from 0 to 15 additional text messages is right here. You'll notice the points are not connected. It's not a line because these are discrete values. You can't send half a text. It's either a text or not. So these are shown as discrete values. C now says if Sky's cell phone bill for a certain month is $22.25, how many additional text messages are there? There are 2 ways that we can figure this out, and now it becomes obvious why they decided to graph up to the first 16. Because each Y value, if you look at it, is equal to, well, I got 4, like 20, 1, 2, 3, 21, which means that each of these is worth a quarter, like 25 cents, which means that 22.25 is going to be right here. So one way that I could do this, if I were to graph all the way up to the first 16 messages, I could interpolate from my data. So I see 22.25. This is 22.25. And I'll check how many text messages is that? Well, going straight down my graph, that's 15 text messages. So that's one way I could have done it. The other way I could have done it is by doing something that we did similar that we did last time in example number 2. We could instead make an equation. So since it's already got the text here, may as well do it this way. The total charge is 22.25. So the function at n is equal to 22.25, and we're trying to figure out what n is. So I'm going to rewrite it as 22.25 is equal to, let me see if I can get a shade up to try and get your eye in the right place. There we go. So starting at the line there, so 22.25 is equal to 0.15n plus 20. So 22.25 once again is the overall cost, and we're trying to solve for n, the number of text messages. First thing I need to do is subtract 20 from both sides. When I do that, the 20 on the right gets canceled out, and I have 22.25 minus 20, which leaves me 225. And 225 is equal to 0.15n. And then I just have to divide both sides by 0.15, and I'll find n. So 0.15 divided by 0.15 is, of course, just 1, leaving our n. And on the left side, 0.25 divided by 0.15 gives us the answer of, surprise, surprise, 15. Either way we do it, we find that Sky's phone bill includes 15 additional text message charges. Luckily, over time, they decided to stop charging you for incoming texts. You still get charged for outgoing text sometimes, depending on your plan. Usually just to like the United States or something like that. Anyway, in summary, all functions are relations. But not all relations are functions. They have to, or the only way that they're classified as a function is if each value in the domain, each independent value, if each x value has only one y value. Or the fancy way of saying it, each value in the domain corresponds to exactly one value in the range. Each function has its own formula or rule that is often given using a special notation called function notation. For example, p of x is equal to 2x plus 8 shows that the function p takes an input value, x, multiplies it by 2, adds 8, and outputs the answer, which in this case is 14. And that's it. Hopefully this was clear. If you have any questions, please do let me know. I hope you have a fantastic day, and I will talk to you later.